Okay, area of regular polygons. So the formula, as soon as that focus is there, 1/2 AP. First of all, notice capital A and small a. So again, a capital A always stands for do a math problem. So this is the area of. This A stands for apothem. It's pretty appropriate this time of year because most students have apathy. Okay, good. So apothem, apple. So kind of a hard A sound, an apothem. So we have to talk about what that is. And then the P stands for perimeter. And that's why it works for a bunch of different polygons. Because if you have a 6-sided figure, then your perimeter is of 6 sides. If you have an 8-sided figure, your perimeter includes all 8 sides. If you have a 10-sided figure, your perimeter includes all 10 sides. So this perimeter applies the formula then to every different shape that you have. So we're going to look at a few basics. Now we'll find out what an apothem is. Well, an apothem is this little line here. It's not really a height. If it was a height, it would go all the way to the top of the triangle, wouldn't it? But it is kind of a height. If I thought about this being the center of the figure and cutting the figure up into triangles, since this is a 3-sided polygon, I would have a total of 3 triangles here. With a 4-sided figure, if I drew lines from the center out, I'd have 4 triangles. And obviously then in a 6-sided figure, I would have 6 triangles. So this apothem is the height. It's the height of this one triangle. Well, we already had a triangle there. So this one is a little weird. But why are we focusing on this? Well, because we're really thinking about it related to the circle. We're thinking about if it's a regular polygon, then it fits in that circle. It's inscribed in the circle. The rest of this, then, is all the other math that we've done this quarter. If this is an equilateral triangle, how big is this angle? It's a 60-degree angle. Or this one, or this one. But this line has cut that angle in half. So it's actually a little teeny 30, 60, 90 triangle in here. So it's the height, the apothem then is the height of this little teeny 30, 60, 90 triangle. So that makes sense. For a triangle, we're going to use a height to find a measurement. And then, just to make these problems real easy, let's make all the sides of the triangle, the main triangle, 10. So what does this apothem do to this base of the triangle here? Cuts it in half. So now we have 5 here. But ooh, this is the yucky one. We've got a 30, 60, 90 triangle. We know it's x, 2x, and x radical 3, and that's where the 5 is. So in this particular figure then, the 5 is the x radical 3. Now, like I said, to start off with, we made the side 10 just so it was easy to work with. It was an even number. It's nice, easy number to work with. So the apothem is the x. It's across from the 30. So if 5 is x times radical 3, how do I get just x then? Divide by radical 3. And when I take 5 divided by radical 3, that's not acceptable. So how do I fix that? Yep, multiply by radical 3 over radical 3. So now I get 5 radical 3 over 3. That is my apothem, 5 radical 3 over 3. Yeah, that sucks. Oh well, it just happened. Then R, well, since we are kind of looking at a circle here, what do you think R stands for? Radius. R is radius, and this side is a radius of the circle. That side is the hypotenuse of my triangle. So, if...
Pardon the interruption. Staff, all seniors should be back at this point from the graduates. If you have any seniors not in your class that were on the were absent today, please shoot us an email. Please shoot me an email. Also, if you have a handful that didn't get lunch because they both got back late, please be flexible. Please be. Have a great day as always. Go by.
So, if the apothem was across from the 30, what do we have to do to get the hypotenuse, which is the radius? We have to multiply by 2. So 2 times 5 radical 3 over 3 turns out to be 10 radical 3 over 3. Luckily, we don't need that in the formula. Formula is just apothem times perimeter. And perimeter is easy enough because we started with sides of 10. So 1/2, again, we found our apothem was 5 radical 3 over 3. And our perimeter is going to be what? 30. It's just 3 of the sides. So this one winds up being kind of easy because the 3 will cancel into 30. We're left with 10. So 10 times 5 is 50 radical 3. Or we could have just thought about our equilateral triangle formula, which was side squared radical 3 over 4. So side squared is 100 radical 3 over 4. 100 over 4 is 25. Why do we have 50? Oh, we forgot about the half in the formula. So half of 50 then would be the 25 radical 3. And that's what we would get if we just used the side squared radical 3 over 4 formula, which actually makes much more sense here. But because this is a kind of regular polygon, I just wanted to show you that, yes, you can do the formula for this one. Yucky, and we're not going to. We don't really need to here. So let's look at a different figure then. Again, we'll just make the sides 10 because it's easy to work with. The apothem here would be this line from the center of the circle, perpendicular to the side. Again, it is the height of a triangle. It's the height of these little triangles that are formed when we put central angles in the circle. So if we're looking at this, again, what does that apothem do to the side? Cuts it in half. And what kind of angle do we have here? If a square has a right angle, but we drew in this radius, now we have a 45, 45, 90. And so if this is 5, then the apothem is 5. And the radius is 5 radical 2. Excellent. So our formula then, 1/2 apothem, we just said that was 5, times the perimeter. So what's the perimeter of the square? 40. So 1/2 times 5 times 40. I'm not going to take half of 5. That's silly. Half of 40 is 20. 20 times 5 is? And no, duh, you knew the area that square was 100 in the first place, right? 10 squared is 100. So, yeah, there's much easier ways to find the areas of these shapes than using this particular formula. But I just wanted to show you that this formula works for all regular polygons. And these two happen to be ones that we can do pretty easily because we know about the 30, 60, 90 and the 45, 45, 90. But this is the one we're going to focus on because we don't have a different formula for this one. So for the hexagon, we'll take a look at this one. And Another way to think about these triangles, I mean, we could try to figure out what this angle is, but an easier way is always just to use the central angles. If we take a hexagon, draw all the diagonals, cut it into 6 circles, we have 6 angles here. 360 divided by 6 is 60. Just like up here, if we had done 360 divided by 4, that central angle would have been 90. Or 360 divided by 3, that central angle would have been 120. And then when we draw in our apothem, what does the apothem do to that central angle? Cuts it in half. So guess what we have here? Another 30, 60, 90 triangle, but it's sitting differently than the one in the triangle. So this 30, 60, 90 is sitting with the 30 up at the top. Again, let's just make sides 10 because they're easy to work with. So what did the apothem do to the 10? Same thing as every picture, cut it in half. And that side's across from the 30. So this one's easy. That means the x is 5. That means the apothem is 5 radical 3. And then the radius is 10. Oh, the radius is the same as the side? Well, yeah, what kind of triangles are these when we cut this up? They're equilateral triangles, yeah. So if we make a side of 10, our radius is also 10. So those two things are going to be equal. And then our apothem is going to be 5 radical 3. And as a matter of fact, we could even write a little formula kind of for that. If the side is 10, how did we get 5? Divided by 2. So side divided by 2 times radical 3. That's going to work in this one. Didn't work here or here. That's a different triangle. But in this triangle with the hexagon, the apothem is always just a side divided by 2 times radical 3. So just a couple points, important points then. In the hexagon, and again, this is only in a hexagon, a radius equals a side. Because when you cut up a hexagon, you have 6, what kind of triangles? Equilateral. So let's see if we can work our formula. Our formula, again, is 1/2 AP. We said our apothem is 5 radical 3. And what's the perimeter of the hexagon? 60. And as a matter of fact, some formulas, rather than saying P, I've seen them say NS. Well, what do you think the S stands for? Sides. And N stands for the number of. What is the perimeter? Isn't the perimeter just 6 times 10? The number of sides times how long the side is. Okay, so 1/2 times 5, again, that's not an intelligent thing to do. 1/2 of 60 is 30, and 30 times 5 is... Or you could have just gone ahead and multiplied first. 5 times 60 would have been 300, and half of that would have been 150. So that is the area then of our hexagon. So again, that's the only one that we're really going to focus on because the other ones already have formulas. Yes? Well, 5 times 40 is 200. So, but yeah, we may have divided, we may have not divided till the end, or maybe we divided the 40 first, because you could work it either way. As long as you take half of something, whether it's half of the answer or half of one of the parts, then yeah. Okay, so if you want individual steps for how to do all this, you can go through all of this, but I think just looking at the formulas that we've had, I think that's enough to get what you need for your formula to work it out. So you could start by first cutting the polygon into congruent triangles by drawing the radii. So again, doesn't matter whether it is the hexagon or a pentagon, or I believe we have an octagon here, cutting it into congruent triangles. But we only need one of those triangles to do the math. So that's what it's showing you here. Pull out one of those triangles, and now think about the degrees in the triangle. So we're going to find a central angle. Central angle, again, is always 360 around the center, divided by how many triangles you made. So in this case, it's 360 divided by 6, so that's 60 degrees. In a pentagon, it would be 360 divided by 5. What is 360 divided by 5? Thank you. 72. Or in an octagon, I didn't draw this very straight, 360 divided by 8.
45.
That's 45. Or in a decagon, 360 divided by 10. 36. So we're going to find the central angle. Then we're going to label the angles of the triangle. So again, with a hexagon, they're all going to be 60. In this triangle, well, if it's if it's isosceles, and we've already used up 72 here, since we need the apothem anyway, and that's the next thing, we might as well just go ahead and do this. What does the apothem do to that 72 degree angle? Cuts it, makes it 36. So 36 and 54 and 90 is 180, right? So in this one, if I knew, again, we could make a side of 10, cut that in half. What would I have to do with a 36 degree and a 54 degree angle to get the other sides? Math that we've done. Yes, we would have to do sine, cosine, tangent to work this problem. Could we? Sure. Could I make one single problem the entire exam? Yeah, because it would cover everything. Think about it. You'd have to know about regular figures. You'd have to know about circles and central angles. You'd have to know about right triangles and the angles in a right triangle. You'd have to know sine, cosine, and tangent to find the lengths of the sides. You'd have to know the area formula for this to find the area. Holy shamoly. Yeah, we could do a whole exam in one question. I don't think we will.
Why not?
So the next question then is, again, if we set a side was 10 or something like that, whatever we picked, how would we find the radius? What part of sine, cosine, tangent would the radius be? The radius is this thing, which is the what in this half a triangle? This is the hypotenuse. So if we're using the 36 degree angle, we have the side opposite. We need the hypotenuse. We would have to do sine to find out what the hypotenuse was, which is actually the radius. So we'd have to do sine of a 36 degree angle equals 5 over x. There's another yuck, because we didn't like x in the denominator. It's a little trickier on the calculator with that one. If we wanted the apothem, this line down the center, so we know this is 5, and actually a side is 10. We know this is 5, and we want this line. What sine, cosine, tangent ratio would we need for that?
Tangent?
We'd need tangent of that one. So the tangent of a 36 degree angle would be 5 over, let's call it y. Icky again, but with the tangent at least we could switch that, and we could say tangent of 54. We could switch the angles and do tangent of 54 would be x over 5, but still that wouldn't be very fun. So for that reason, That's why we're not going to worry about these other shapes. They are possible. Now, if this was an honors class, oh, you betcha. You would definitely have to do at least one of these on a test and go back and use all of that other stuff. But we are just going to focus on just the hexagon. And as a matter of fact, if we do a few more of these, I think you'll see that you don't have to worry too much about drawing these pictures and cutting them up and drawing them all out, because there's some easy relationships. First of all, in the hexagon, we said the side and the radius were the same, equal. We just said that back here. Radius and side are equal. And the apothem, even that, we said you could kind of come up with a quick way to get it if you knew what the side was. And then somebody stopped taking notes. Okay, so what if I told you a side of the hexagon was 6? What's the radius of the hexagon? 6. And what's the apothem? 3 radical 3. We just said the apothem was the side divided by 2 times the radical 3. So what if a side of the hexagon was 8? Then what's the radius?
8.
And what's the apothem? 4 radical 3. What if a side of the hexagon is 12? What's the radius? And what's the apothem? 6 radical 3. Side divided by 2 times radical 3. What if a side is 15? What's the radius? 15. What's the apothem? 15 divided by 2, radical 3. You don't mix decimals with radicals. And if we're going to plug that into a formula where we already have a half and we have to find perimeter, probably we could do some simplifying with that too. All right, so if we stick with the hexagon then, it's pretty easy to find the other stuff that we need to plug into the formula. Okay, so that's what we're going to do next, is look at just some review, some general stuff.